Hi class, we are now on 26.3. This is coordination compounds. Unfortunately, this is a kind of long section, but a lot of it is actually just examples to help you. There's a lot of slides here, but I try to give as much examples as possible. So complex ion. This is where we're dealing with transition metals that are ions and they're bound to one or more ligands, and that's the electron pair donor. So we're looking looking at a Lewis acid and base compound. So a ligand is a Lewis base that donates the electron pair to the metal, and the metal has an empty atomic orbital, or d orbitals in this case, to take on those electrons. Ligands bond covalently because they are sharing electrons in this case, and that's where the fancy coordination covalent bond or complex, it's because these are coming from the electrons that are being donated are coming from the ligand and not the metal itself. So when a complex ion combines, there may still be a charge on the overall of the ligand because some of the ligands are not neutral, so they will give a charge on top of what the metal ion complex has. So in order to balance this out, they have counter ions, and counter ions associate electrostatically. So they're not covalently bonded, but it's their attraction, and they're placed outside of a bracket when we start. We're going to do nomenclature in this section. They are placed outside of the bracket, and the ligands that are attached to the metal complex are placed inside because that shows that those electrons are being shared. However, the counter ions are on the outside, and it'll match to balance how many of a charge that is needed to make this a neutral compound. And when they make this a neutral compound, it's a coordination complex is what it's called. So here's a perfect example where we have the central metal ion, and it's got a positive charge to it. And then we have ligands that come in and attach it, but this still ends up being a 3+ overall. So it's got ammonia compounds that come in, and I do not believe ammonia compounds are neutral compounds. So that's also going to add to a charge to this. So in order to balance this 3+, you get 3 counter ions, and that makes this a neutral compound. So we have our central metal, we have our complex ion, which is the whole thing. Then we have the counter ions, and with all of this makes the coordination compound. So when we deal with coordination compound, there's 2 different types that we're looking at. So the central metal atom has 2 different types of interactions. They have the primary valence, and that is the oxidation number on the central metal ion itself. Then it has a secondary valence, and that has to do with the number of ligands, which are molecules or ions that are bonded to the metal. So we need to look at that as well, and they're usually in the super subscript. And that's called the coordination number. Coordination numbers can range from 2 to 12. The most common are 6 and 4. And the coordination number, again, is the number of atoms that are bonded, or ligands, are bonded to the metal. So if we look at this compound here, we have cobalt 3 chloride, hexa, I don't know, this is not a hydrate. So I don't know how to actually say this part right here. I got ahead of myself. But see the 6, that's the coordination number because that's the number of ligands that are bonded to the metal. So you have to look inside the bracket, and inside this bracket, this is actually bonded, and the 3 chlorides are the counter ions. So that's what we're looking at here. What's attached and what's not attached. And here again, you can see from different slides, the same thing. It's breaking it down, but it's looking at what is the primary coordination, which is the primary valence in your book. When this slide, it's from another slide. So they're calling it primary coordination, and secondary, but in our book, it's secondary valence. All right, so let's determine the coordination numbers of these and determine which groups are in the primary and which are in the secondary. So if we look at this first one and break it down, there's no brackets. So that means that the water ligands are in the primary. They are primary valence, so they are ligands that are attached to the metal, and the coordination number is 6. So there are no counter ions. Here we look again, there's no brackets, so there are no counter ions. They are just the ligands that are attached to the metal ion, and we can see that we have a 2 and a 2, so the coordination number here would be 4. We have 2 ammonias and 2 chloride ions. On this one, we have brackets. So here we have the transition metal, and the coordination number, the ligands that are attached to it are 6, and they're inside the bracket. So the coordination number is 6, but we also have counter ions, and we have 2 of them for the potassium, and they are on the front, listed in the front. You'll also see them listed in the back, but because these are positive, they're written in the front. Okay, so complex ion formation. We're looking at a Lewis acid-base reaction. Remember, we're looking at an electron donor and electron acceptor. That's in the terms of Lewis acid and base reactions. So this is a coordinated covalent bond, and what that means is that the bond is formed. So we have a covalent bond that's formed. However, it is because of the electrons that are donated by a ligand and not on the metal itself. So the metal has an empty orbital, and the ligand donates those electrons, and that creates the covalent bond. So this is a complex ion, so that's why it's called a coordinate covalent bond. So and then we're also looking at not just the ligands itself and how it coordinates, but are they known as monodentate or bidentate? And I believe it's in Greek or Latin, that terms means teeth or teeth-like. So a ligand that forms one bond with a metal is monodentate. And that means it's just attached in one place. It's got one thing that's going to form the bond with that metal. So ammonia can only form one bond to a metal, whereas others have multiple donors and can bond with lone pair electrons that can bond to the metal. If it has two, then it can form it's called a bidentate ligand, and a bidentate. So in this case, we look at ethyl. This is, even though this is ammonia here, we've got lone pairs that are right here. This is ethyl diamine. So this whole compound here is ethyl diamine. It's got two different places that it has lone pairs on them. So this is a bidentate ligand. Lone pairs on different atoms that are separated enough that they can both bond to the metal. So this huge thing will come in and bond to a metal in two different places. And then they have oxalate, which is short for ox, or ethyl-diamine En, and it's the same thing. They have bidentate, which means they're usually big complexes, because they have to have enough distance so it will allow these two lone pairs to attach to a metal ion in different places. So here we have hexadentate, and that's 6 donor. So you can see all the lone pairs they've highlighted here. So this is ethyl-diamine tetraacetate, EDTA. And you can see where it's got different lone pairs, which will allow it to attach, and it's huge, so it has enough distance to allow that to happen. And polydentate is more than 2 electron pairs that will bond with a metal. So here are some of the common ligands, and this is where I have a lot of slides, because some slides give some information and others give others. So for in this case, it tells you what kind of coordination, how it bonds. Is it one bond, or can it bond in different places? It tells you the ligand name, because as you can see, these are now different, which we'll cover. But this is amine. Water is aqua. We have a nitride, which is azeto. We have a bromine, which is bromido. And, like carbonyl. Carbonyl is discussed over and over in organics, so you'll always get used to carbonyl. You will not get away from that. And which are the donor atoms? Which one is donating the electrons? So in this case, you can see here, there's more. You can go through these. And then these are from another slides, and you can see the names are different. And then these are from our slides in our book, and I kept these as well because they show you the diagram of them, of what they actually look like, so you can see the electron pairs. So this one covers more information that we haven't covered yet, but this one's actually showing you the ligands themselves. So that's why we have a lot of slides in this. So predict whether these ligands are monodentate, bidentate, and so on. So we have fluorine. Let's look at fluorine. We have a fluoride ion. So it has 4 pairs of electrons. However, it can only make one bond. So it is a monodentate. So it only bond in one place to a transition metal. Yet, if we look at this other one, which is bis-dimethylphosphinoethene, and this has, you can see it's pointed out in red arrows that it has 2 lone pairs. So this is a bidentate, and it can bond in 2 different places on a metal ion. Okay, so complex ions with polydentate ligands. Bidentate, polydentate ligands are known as chelating agents. When I worked in the lab, we always discussed chelating compounds. For what we needed stable compounds. And these are unusually stable with the metals. So sometimes when we're doing reactions, we need chelating compounds and chelating agents. So one thing, they are complex ions with bidentate or polydentate ligands, so they wouldn't apply to monodentate. They are known to be extremely stable with the metals. The coordination compounds are generally far more stable than with monodentate, and the chelate effects is explained in the terms of entropy. So this is what makes it more stable. Remember, entropy, an increase in entropy, when we're looking at if a reaction is going to go in forward or direct or reverse. Well, now we're looking at instability, and this is an increase in number of particles increases entropy, and that tends to be a chelate effect. So here is a lot of information, but I just want to point out why entropy plays into this. Here we have pyridine, and I used pyridine over many years in my lab, and then we have bipyridine. And you can see here the balanced reactions, which is exactly what I want to show you. How does entropy play into this? Well, let's count the moles on each side. We have, if you see here, it says in the reaction, we're looking at this one, there is no change in the number of moles or particles on these sides. So it's 7 on one side and 7 on the other. However, when we look at the bottom one, we have 4 moles of reactants, but we have 7 moles of products. So this is an increase in entropy. And that also has that also can affect the chelate, determines about the stability with chelating. So that's the only this has a lot of words to it and stuff, but I just want to point out that the bipyridine is a bidentate and pyridine is a monodentate. All right, so the next section in 26.5, you're going to look at geometries, and that has a lot to do with how the ligands attach and so forth. So, but we're going to briefly discuss it here. So compounds with coordination numbers of 2 have linear geometries. That's because it only has 2 places. Compounds with coordination numbers of 4 have 2 possible geometries. They can either have a tetrahedral or a square planar. And some of these kind of helps out. So if you have an ion with a D10, they tend to form a tetrahedral. And if you have something with a D8, they tend to form a square planar. And most 6 coordinate complexes have an octahedral geometry. So here are some examples so you can see it. We have a coordination number 6 tends to be an octahedral with an example here. A tetrahedral can have a 4 and a 4, but depending on if it's a D10 or D8, D8s tend to be square planar, D10s tend to be tetrahedral. So that's got 4 ligands attached, and then you can see at the top there's 2. So it's not really going to have anything more than linear because it can't. So here's just an example of how these attach, and you see how complicated it starts looking. So we have 4 ammonias, but you see how it's got this nice figure like a star kind of thing that attaches. But so it goes from this with this, and it comes into something very complicated. And you know, this is not showing all the little terminal hydrogens on it, but that's pretty much with the tetrahedral geometry. Determine the likely geometry of the following coordination compounds. So with the first one, we got a coordination number of 2, so the shape is linear. That's kind of easy. Now we have, with the coordination of 4, we have to look at the essential metal itself, and it's got a D8 electron configuration, so this is going to have a square planar geometry. All right, so now we're going to get into naming, and this is where I was going to separate this into two videos, but I might have to refer back to the prior ones, so that's why I didn't want to separate them out. We name these differently. So as if you didn't have enough of naming, now we're going to name even more. And it's different. The names of ionic compounds include a name of the cation and a name of the anion. To name the complex cation or anion, we have to determine the oxidation state of the metal. So there's a few things that are a little different here. The overall charge of the complex is the sum of the charge of the metal ions and the charges of all, the metal ion, and the charges of all the ligands. So I'm going to show you how to do that. So here we want to first get it says here to get the oxidation number of the metal. So we're looking at the oxidation of the metal. So in this case, it's determined to be a +3. Why is it determined to be a +3? So just like if we remember the oxidation reduction rules, well, now we're looking at the ligands themselves. And chloride ion has a negative charge to it. So that's where this -1 comes from, and we've got 6 of them. And we take this charge, make it equal to that, and once we are done with that, our X is a +3. So the oxidation metal itself is a +3. So this is very similar to redox reactions. However, we have ligands, and there's a chart in here, and you're just going to go by the chart or the charge on it. It's really not that difficult. So here is the chart. So you're going to be asked about some of these, so you should make a note about this page, because this is a -1, -1, -1, -1, -1, 2, -2, and you can see, and then we have neutral molecules, so that would be a 0 for these because they are all 0. So neutral, I even highlighted it so you can see neutral and anions. Okay, so determine the oxidation state of the metal in each compound. So with the first one, we're looking at the metal itself. So with palladium, we have cyanide, and that is a -1. Why? Because if we go back, you can see it's here. It would be called now cyano in this complex, and it's got a -1 charge. So it's going to, you're going to solve for that. We take the -2 on the other side, and this palladium is a +4. So that's the oxidation state of the +4. And if we look here, that's the first thing we're trying to do is determine the oxidation state of the metal. Okay, so in this case, it's a +4. So now we look at nickel. Nickel has carbonyls, which is carbon monoxide, but it's called carbonyl. And it's a neutral molecule. So because it's a neutral molecule, it's going to be a 0. I jumped too far ahead. And that means that the nickel oxidation state is 0. Now, if we look here, we have manganese. And manganese has 5 ligands of one type and then 1 ligand of another. So we have to look at all of these. So we've already discussed chloride. So it's a -1, but we have 5 of them. And then we have NO3, which is nitrate, and I don't know what it's called on here, so let's see. It's not even listed on here. I think that's why I put it on there, because it wasn't listed on there. And it has a -1 charge. So if we're looking at the -1 charge, we have to, because see, this one has a counter ion on the outside. That's the difference here. The other ones didn't have the counter ions, so we had nothing else to determine what the oxidation state of the metal is. In this case, there is. So that's where ammonia is a 0 charge, and then the nitrate is a -1. Factor all of that in, and our oxidation state for manganese is a +6. So now let's do the naming. Name the ligands first. So for ionic ligands, the ending E changes to O. So chlorido, I know I'm not saying this right, carbonato or carbonado. Neutral ligands have special names of aqua and amine. List multiple ligands alphabetically. So aqua then is named before bromido. So we're going to look at the new names, and then you're going to alphabetize those. Add prefixes to indicate more than one type of ligand. So we're going to use di, tri, tetra, penta, hexa. So hopefully those are very, you understand those. For ligands that have names that include Greek prefixes, so triphenylphosphine, so that ligand is triphenylphosphine, then we would use bis, tris, tetrakis, pentakis, hexakis, and enclose the name of the ligand in parentheses. I know some of this seems overwhelming, but it has to be learned. Ignore the prefixes when listing ligands alphabetically. So of course we're going to go through some of these. So name the metal last. So the metal is last. Name all the ligands first. Metal is last. If the complex is positive or neutral, the metal is named as normal. So in a complex of an iron 3, we would name it iron 3. However, there is a different name when it is negative. So the metal name ends in 8. For example, a complex ion of cobalt. So this would be a cobalt 2, but in this case it's going to be negative, so it'll be cobaltate. And why is it going to be negative? Because that's where we're going to look at the whole compound overall, and then you can see if it's positive or negative. So in this case, the 8 instead of leaving it the way we normally know how to. So here is charts, more charts, so that's why there's a lot of slides here. Gives you the name of what it would be, what it normally is, how you know it. So nickelate, platinate, zincate, which is zinc. So, I mean, some of these are weird at first because, well, you know zinc, so it's zincate. It's an ionic complex. So how do we know how to use this? All right, so let's look at this first one. We have cobalt with a coordination number of 6 with ammonias, but we also have a 3+ charge on the outside. So how do we know how to name the metal? We got to know if it's positive, how to do this. So in this case, ammonia is neutral, so that's a 0. The metal ion is a +3, which we've already covered. This complex is not negative, so we would use cobalt 3 instead of cobaltate. So this is hexaamine cobalt 3. Where's the hexaamine? Well, 6 amines in front, and ligands are named first, and then cobalt, and we don't have any counter ions with this. So we don't have to worry about the counter ions. However, if you jump to the next one, we have 3 counter ions to take care of that plus charge. The chloride ions are counter ions. They are not exactly attached, so we don't consider them ligands. So now it is hexaamine cobalt 3 chloride. All right, so here we go, some more examples. Potassium is on the outside, the counter ion. There are 4 cyanide ligands with a negative charge. So the metal is platinum, and we need to know what the oxidation state. So you can see we have 2 counter ions with the +1. We have X as the platinum. We don't know, even though it says what it is right there. If you didn't know, this is how the steps. We have 4 -1s, and we make it equal to 0. So once all of this is worked out, we have a +2. So the metal is a +2. The complex, the part in brackets, is negative. So we add the 8 to the metal. Why? Because we needed 2 counter ions that are positive to make this a neutral molecule. So if we didn't have this here, you would see that this is overall here as a negative. We know that this metal is a +2, but we're looking at the whole overall complex, and that is negative. So that's where the +2 comes in to make this a neutral. All right, so over here, we have water and Cl- ligands. Bromine is a counter ion, so if bromine is negative, then this must mean that this is positive. If this is positive and counter ions are needed, that means that this is negative, and that's where the change of name is going to come in. So in this case, we determined that the copper is a 2+, but we need to, and so that's not negative, so we don't need to add the 8, and just having the bromine, which is negative on the outside, tells you that that's not the case. So we name everything first alphabetically. We have tetra aqua chlorido, because we only have 1, copper 2 bromide, and bromide is the counter ion. All right, so let's name the following coordination compounds. So I'm just going to jump into it. So in this case, we have a counter ion, but it's positive, so that's where the sodium comes from. We have 4 coordination, 4 cyanides, so it's tetra cyanido nickelate, and we have positive counter ions, so that means this compound is negative, so that's where the 8 name comes from with the 2. Over here we have 2 negative ions, so this is positive, so it's going to be named how we normally do. So in this case we have 3 ethylene so we have ethylene diamine, which contains a Greek prefix, so we have to use an alternate prefix. So because it has a di here, and we can't use that. So this is where the tris ethylene, because we have 3 of them. So we have to use 3. So does everybody understand what this means? Because this name has a Greek prefix with this di, even though it's in the middle, it's got a Greek prefix. So you have to follow the alternate prefix rules. So in this case, we can't use tri here. We have to use tris. So tris ethylene diamine iron 3 chloride. And again, here's some ligands. This is from our page. Neutral, so you know which ones are zeros and the names that go with them. And the negatives and the charges and the names that go with those as well. And metal, if it's an ionic form, it tells you how to name them. And then here are just more examples for you to go through. If you needed to go through and you're a little hesitant on how to do this, this is showing you how to name them and the steps that we went through. And then these are examples from the book itself. So name the following compounds. So this is how your book is breaking it down. So identify the cation and anion. First name the simple ion. In this case, chloride is chlorine. The ion is chloride. Each ligand has a name. So we have aqua and we have chloro. Name the metal ion. We determine the oxidation state is 3+. So this is penta. Remember, we do in alphabetical order. Penta aqua chloro chromium 3. It's a positive, so this is 3. But we're not done because we need to name the counter ion, and that is penta aqua chloro chromium 3 chloride. All right, and then the next one, very similar. It's showing you how to break it down. Is it going to be negative or positive? Looking here, you can see that this is positive, so that means that this is a negative compound. So we're going to have to use the 8 ending. Cyano is cyanide is now cyano. We have iron 3, but this is ferrate because it's anionic. And we named the compound itself before we named the counter ion. So this is hexacyanoferrate 3. And then we have potassium, which is a positive, it's on the front. So potassium hexacyanoferrate 3. So coordination compound is any complex ion or neutral compound that contains a metal that is complex by ligands via a coordinate covalent bond. That means the ligands are donating the electrons. The metal center and covalent bond ligands constitute the coordination number that has a primary and a secondary. And the primary, the coordination number, is the number of atoms that covalently bond to the metal itself. Other groups that interact with the metal or ligands via intermolecular forces are part of the secondary. Ligands are classified as monodentate, bidentate, or polydentate that are attached to the metal. Bidentate and polydentates are also known as chelating agents. They are very stable, and that has to do with an increase in entropy. And certain geometries of coordination compounds include linear, tetrahedral, square planar, and octahedral. The oxidation states of coordination compounds are determined in a manner that is analogous to the oxidation states of ionic compounds. There's 4 steps. You should be very familiar with these steps. Follow through them if you have problems learning how to name these. They don't change. That's the good thing. It just will take a little while to get used to this. But it's not overall hard because you guys hopefully have remembered how to be naming things.